afternoon is going to be why would you want to use virtual prototyping? We'll look at some workflows for designing luminaires in software, talk about some of the analysis tools you can use in software for design verification. We will also talk about optimizing luminaires in software. This is a section where using an optical design or an optical analysis program can really give you some good benefits. We'll do some examples. I'll show you some examples, walk through those, and then we'll wrap it up again with the question and answer session at the end. And as Robin mentioned, please feel free to type any questions you have in the questions box, and we'll address the questions at the end of the webinar. So the question is, why would we want to use virtual prototyping, say, versus making actual physical prototypes? When we're talking about luminaire or lighting design applications, generally when we use the term virtual prototyping, it means we're going to be using some type of optical design and analysis software. The advantages of doing it this way, it's easier to make multiple designs in software compared to actually making physical prototypes. The luminaire performance can be checked out quickly and easily in software. Multiple designs can be compared quickly and easily in the software environment. It's also faster to make multiple designs and compare them to each other versus making physical prototypes of those designs. It's generally better to make your mistakes in software. Make the mistakes where you can just make a few mouse clicks and make some changes as opposed to making a mistake with an actual or a physical prototype. It's also less expensive in terms of making mistakes. There's a cost of time in redoing things, but you're not invested in actual hardware typically at this point. That being said, there also could be some disadvantages to using an optical design program. One is the initial cost of the software, and that can be substantial in some cases. There's the ongoing cost of the software, things like maintenance and support. There's a learning curve. With any new program or any new process, there's a learning curve, and how long is it going to take you to learn how to use the software effectively and efficiently? Generally, you want to have sort of an initial correlation of modeled versus actual results. When you're first starting out, and this was my process, almost 20 years ago when I first started using, in this case, TracePro, it was sort of a trust but verify relationship between me and the software. I would do my designs in software, but I would still try to build a prototype of those, compare them, and kind of have some lessons learned. And then going forward, I was eventually able to trust and benefit from doing more and more in the software as opposed to having to go to that, make the prototype, bring it into the lab, measure it, and then try to figure out what went wrong. Another thing in doing things in software is you need to have accurate property data. And this is things like, source models, properties with like scattering and surface roughness, material properties with transmission, absorption, refraction, index of refraction, things like that. There's an old saying I remember when I was taking some programming classes that garbage in equals garbage out. It still applies, even today in things like this. And related to that, needing to have accurate property data is the fact that sometimes it may cost money. You may have to send samples out to be measured. We try to have good catalogs in the software, but sometimes somebody's using a proprietary or unique material. And in that case, they may need to send it out to get some measurements made to get the optical parameters measured. So let's take a look at typical workflow for designing a luminaire. And this is a simplified workflow, and I'll go into a little more detail here in the next couple slides. But we could design the luminaire in a CAD program, or in a lot of cases, you can do it right in the optical analysis software. If we designed it in a CAD program, the next step would be actually to import that model into the software, whether it's an SAT, a STEP, an IGES file, or some other form of CAD file. Apply material and surface properties. I set this up using LEDs as sources, but setting up your sources, it's not unique to LEDs. It would apply whether you're using an arc lamp, an HID lamp, a xenon lamp, a fluorescent lamp. You would need to set up that source accurately, whether it's using something like a surface source property or downloading a ray file from the manufacturer. And then you'd run a ray trace. You'd analyze the results. From those results, if necessary, you could export an IES or an LDT file. Excuse me. Basically a photometric file that can also be used by other programs, such as Dialux, Lightstar 4D, AGI 32, programs like that. And then as a last step, you could also generate a lighting report that you could pass on to your customers or your vendors. And here's that process, but now just done graphically. Excuse me 1 second. Okay, sorry about that. Looking at that process graphically, here we have a design in SolidWorks in this case. It was then exported in this case to TracePro. We applied our properties, set up our sources, ran the ray trace. We exported an IES file, and then from there we were able to generate a custom lighting report based on the IES data from this system. Now, if we go in a little more detail and sort of look at a more typical workflow, we'd start out with a project specification or a design goal. Many times then we'll go in, next step is calculating the source requirements. If we're using LEDs, how many LEDs do we need? What kind of space do we have to put them in? What's the budget for adding LEDs to the system? From that, we can then choose the appropriate source. Then we can make a model of it or get a ray file if it's available. In this case, if we're optimizing the design, we'd set up that initial optical element, whether it's a lens or a reflector or a light guide, in the interactive optimizer. Then we'd set up the model in the software, including things like the optical elements, any sources, any targets, any mechanical structure that could have a role in the process. We would then set our goals or targets. What are we looking, what are we trying to get this system to do? Is it uniform lighting? Is it a particular beam pattern or a specific illumination pattern? We then run through the optimization process. We then step out, we analyze the results. If we're happy with that, we could then output that design as CAD files, drawings, IES files. We could at this point make a prototype. And then we're probably usually going to want to measure that prototype, vary the design goals, verify that it meets the design goals. If necessary, and this a lot of times is the step we hope to eliminate with software and optimization, is updating the model and making changes. And then the last steps, what everybody hopes to do, deliver to the customer, and then get paid for the job. And that could be an external customer, could be an internal customer. So when we're doing design work and optimization in software, it's great to be able to take advantage of the analysis tools that we have available. So the analysis tools in optical design and analysis programs allow the users to test their designs in a virtual environment. You don't need to bring a prototype into the lab and measure it and the time it takes to do that. This can be accomplished much faster than setting up a prototype for measurement in a lab. You have the setup time, you have the time it takes to take the measurement, you have the time it takes to correlate the data, analyze the results, things like that. Also, multiple types of measurements could easily be made. Illuminance, intensity or candela, luminance, total flux, efficiency, uniformity, colorimetry, photorealistic rendering. Now, another advantage of software is if I'm doing these measurements, I don't have to drag out a photometer to measure illuminance or intensity, or then get a luminance meter to measure luminance, an integrating sphere to measure total efficiency or total flux, or a colorimeter to measure color, the color characteristics, or a photometer to measure uniformity. I don't need all this equipment and the time it takes to bring that into the lab, set it up. Also things like keeping track of calibrations and where all that type of thing that goes with that equipment. The results from the software can be saved as IES and LDT files. You can then generate lighting reports using the data from the analysis. And another nice thing you can do with the software is you can easily switch between radiometric and photometric units. In most cases in lighting applications, you're going to be looking at photometric units, lux, lumens, candela. But sometimes if you're doing an infrared application or UV curing, you might need radiometric units as well. In which case, if you're doing measurements, you now need to change detectors or change filters on the detectors and go back and repeat measurements. So it's very easy in software. It's just a little switch that you can turn on and off to change the units. So some of the different, or the more common tools in terms of analyzing results in software. One is the Illuminance Map. And I'm going to concentrate mainly on the photometric units, as those are the ones we typically use in lighting applications. But just note that all of these tools, really, except photorealistic rendering, also have radiometric versions as well. So the Illuminance Map is used to display the spatial distribution of light on a specific or selected surface or surfaces. So here's our little desk lamp example, and we have light shining down onto what would be the desktop. We can also see that here, another version of the Illuminance Map, where it's also going to give us information like the efficiency, how much flux is hitting this target versus the flux emitted by the sources. We can get profiles as well for horizontal and vertical beams. So as I just mentioned, I sort of jumped ahead there, but the Illuminance Map can also display things like total flux, minimum, maximum, average illuminance values, flux on the target versus flux emitted, and profile plots. You can also, in many cases, switch these Illuminance Maps over to display CIE data, things like CCT, correlated color temperature, or the CIE color coordinates, either in X, Y, or U prime, V prime space. So we see those two CIE plots here. You could also, or you might be interested in the angular distribution or the intensity plot. So it's intensity of the light as a function of angle. And these are the plots that we use to generate IES and LDT files. I should mention, anybody that's not familiar with IES or LDT files, IES is Illumination Society of North America. LDT is the file extension for a file format called illumdat, which is more common in Europe as opposed to IES being more common here in the US. But both of these can be generated from these candela plots here. The IES and LDT files can be used to generate custom lighting reports or to export that photometric data to architectural lighting design software. As I mentioned, things like Lightstar 4D, AGI 32, Dialux. These programs all typically work with IES or LDT files, and those can easily be generated in the software. You can also look at things like if you're doing display applications, you might be interested in luminance or photorealistic rendering to show the luminance of the luminaire or light source and a lit appearance of how it looks to a viewer. So here's a light guide. In this case, it has our name and logo on it. There's a white LED on each end, and then there's a red semi-transparent paint filling in the letters that have been engraved into the plastic light guide. And here we have a luminance plot where we're seeing values in nits or candela meter squared. And then here's the photorealistic rendering version. And we can see, because the back of the light guide is clear, smooth plastic, we have reflections off that, sort of a ghost image of the lettering from the back side of the light guide as well. So now I want to talk about optimization. And optimization is where I think where software packages can really start to come into play and their usefulness. So we can start off with a question. What is optimization? Well, courtesy of the Merriam-Webster Online Dictionary, it's an act, process, or methodology of making something, such as a design, system, or decision, as fully perfect, functional, or effective as possible. In this case, we're typically talking about designing things. What are some of the parameters that we could optimize? Well, we could look at things like geometry, curvature, facets, position, angle, spacing, thickness. We can optimize properties, select the best property for a given application. So there's a lot of different parameters and features that can be optimized. And just some little examples here showing things like a curved light guide with a prismatic or faceted type surface on it here. And this light guide is actually curving in 3 dimensions, but things like the curve could be optimized, the facet or prism angles here could be optimized to some goal. This is a reflector with an LED source, and in this case it has curved facets on the inside, and we can optimize those curved facets. We could change the curvature of them, things like that. This is photorealistic rendering. We're seeing some specular highlights off of those curves. If we have a TIR hybrid lens, we could use an optimizer to optimize the shape of it. You know, what's the curvature on the side, the shape and curvature of this input section, as well as the sort of the refracting element right here on the front. And then another example, and this one we'll look at a little bit later, but it has a reflector and an LED with a lens that's designed to emit light to the side, so we can improve the collection efficiency of the reflector. So in terms of optimization, this is what a lot of people would like to see. A button on their computer that says easy. You just hit the button, it goes off and does everything. Or as our tech support manager here has told me several times, what people really want is the make my system button, where you tell it what you want, hit a button, and it goes off, makes your whole system. Unfortunately, we're not there yet, but we hope with the optimization tools and the software, what we can do is make the process easier. So why do we need to do optimization? What if we looked at an example where we say we could just do brute force? You know, in software, we could just try all different parameters. So the goal in this case is to optimize the reflector shown below here. And it has an LED array as a source. The optimization goal in this case is even illumination in the central 2/3 of the target region. And this variable, or this reflector, it's a rather simple design. All it has is a single control point. This inside point here, it can move within this range where this box is here. And basically that's 40 millimeters wide and 100 millimeters high. This outside control point is linked. It's a pickup variable, as it's called, of this inside point. So they always move together, just used to maintain sort of a constant wall thickness. It's not a variable of its own. Now, in an actual design, we'd probably have additional control points here, allow the curvature to vary over a larger range, different types of curvatures. But again, our control point in this case can move plus or minus, plus or 40 millimeters in Y, 100 millimeters in X. If we wanted to scan that entire range in 1 millimeter increments, we'd have the number of increments would be 41 times 101, or 4,141 increments or steps. If we set our ray trace time to be 1 minute for each iteration, it means it's going to take about 70 hours to complete this process. If we wanted better resolution, and we said we want to scan in 0.1 millimeter increments, it's now going to take almost 280 days to complete the process. And here's the optimization log. We can see the variable here changing 1 millimeter at a time, so 39 by 83, 39 by 84, 39 by 85, and so on. And here we see our results. And the reason we see this this is the error function on the left versus the iteration count on the bottom. The lower the error function, the better the result is. And the reason we see this sort of sawtooth type pattern, if I go back here, the actual solution is down here somewhere, the best solution. So the process starts up in the upper left corner, and as it comes down, it gets close to a good solution, but then it comes back up here, it gets worse again, now it comes back down, and each time it steps over 1. And that's why we see this sort of getting better and better, and then getting worse. Now, what about applying some intelligence to this? And we can do that by using an optimization algorithm. In this case, we use what's called the downhill simplex method, or Nelder-Mead. And now the time was reduced to about 2 hours and 20 minutes. With the caveat is, in this case, I actually traced more rays. And this time was on my previous computer, so on current newer computer, it was probably be just over an hour for this process. And to show this, I'm just going to show a quick video here. And what this is this is the process as it's happening. Now this is speeded up. It's not in real time, but we can see the control point moving around. We can see the error function changing. And as it's going through different iterations, I did a bit of a picture-in-picture here where I can see the Illuminance Map changing. And the lower this number here on this trend chart, the lower the error gets, the better the result. We can also keep track of the best results so far is this one highlighted here in red. It's about to scroll off the screen. But what you can notice here, even just 35 iterations in, that even after about 15 or so, we had a good solution. It's not changing much. And you can see now that the actual point is only changing by very small increments. The error function is barely changing at all. So it's just trying to find the best point in that area. And let's see, I can just stop this now. Okay. So that's just a little bit of a video to show you the process and how it works. So you notice it didn't scan the whole area. It used some intelligence, some smarts, to find out where is that best point, where does it want to go to. To do that, it uses what's called an optimization routine or an optimization method. Generally, we have two types of optimizers in software, and they appear in different types of software and have different roles. But first is what's called a global optimizer. And that's used to search the entire solution space to find the best solution based on that optimization goal or merit function. And you typically see this in lens design programs such as Oslo, Zemax, Code 5. And you'll see names like Global Explorer, Adaptive Simulated Annealing, Global Synthesis, Hammer Optimization. A little bit different from that is what's called local optimizers. And local optimizers are going to find the solution closest to the starting point of the optimization process. And one thing you can do as a check in this case is if you change the starting conditions, you can change the results of the optimization process and see if you found the best answer. This is the methodology typically found in illumination design programs, things like TracePro. Some names for this, you'll see downhill simplex or Nelder-Mead, damped least squares, Powell's method, and there's probably others out there as well. Okay, now, just like to sort of the last section of the webinar here, spend a little bit of time going through some examples. And just as a reminder, I think that's popped up on the chat as well, but anybody that has any questions, please feel free to type them into that chat box or the question box there, and we'll take a look at those at the end of the webinar. So I've got 3 examples I'd like to show you. One is a TIR hybrid lens. And I want to make a comparison of a manual versus an automatic optimization. Then we'll look at a combination of an LED lens, a side-emitting LED lens with a reflector. And we can look at that in 2 ways. Do we optimize one part at a time, or can we optimize both of them at the same time? Are there advantages or disadvantages to doing it one way or the other? And then lastly, you'll take a quick look at a curved facet reflector, something that has some complexity and things like that. So here's a TIR hybrid lens. And if somebody's not familiar with the term, generally it means you're using total internal reflection on the sides of the lens to take, let's see, can I turn on a pen here? Yeah. We're using TIR on the sides, so any light that comes in here is reflected up like that. And then it also uses a refractive element right here in the front, so light coming in like this is then also, those should be straight, but something like that. There we go, erase that. So it's a combination, it's a hybrid of a total internal reflection lens and a standard refractive type lens. And usually these side profiles are made what's called the profile is a CPC, compound parabolic concentrator. The initial design for this was something I had done for an example several years ago. And I spent 3 or 4 days optimizing this by hand. Basically, making a change, running a ray trace, looking at the results. Make a change, run the ray trace, compare that result to the previous one, and go through and slowly kind of zero in on a design. And I was fairly happy with the result. I got 18 watts per steradian for an intensity. It was about 87% efficient. Note this was a paper design. We didn't actually make this lens. It was just a design exercise. Now, not long after that, we started introducing our first optimizer. So one of my thoughts was, well, what if I take that design and I bring it into the optimizer and see if I can improve it? So here's the initial lens. In this case, I used a bitmap of that lens drawing as a profile or as a template. I drew the image in here, the profile of it or the segment, and then I applied variables. Each of these points here is a variable, and there's 12 variables, and each of them can move in 2 axes, Y and X in this case. And these little crosshairs kind of show how far they're allowed to move. In our optimization utility, there's also the ability to draw rays. So here's some rays sketched from the source, showing their path through the system. And if I was to go in and actually move these points, the ray trace in here will update in real time. So we can use that as an initial design tool to get our design, our starting point, close to where we want to be. Now, after that was set up, turned it loose in the optimizer. Total time spent optimizing was 1.5 hours. I should note this was in an older version of TracePro before multi-threading was added. So this time now would probably be down about 1/2 hour for this optimization process, maybe less with a fast computer. But we can see now the intensity is up to almost 37 watts per steradian versus 18. So we doubled the intensity, and we had a small gain in efficiency as well, going from 87 to 90. And the goal in this process was to try to narrow the beam up to get the intensity higher. And we can see it did just that. It narrowed that beam up, intensity doubled. And here's the before and after. Red is the trial and error, or the before result, and black is after the optimization. In a lot of cases, the changes are relatively minor. And with the trial and error process, I don't know if I ever would have gotten there, even if I spent 10 days or a month trying different variations. So in this case, the software gave me a really good answer in a relatively short period of time. Now, the advantage here was we were starting with a design that was close to the goal, so the process, I think, was fairly efficient. But let's take a look at something that adds maybe another layer of complexity. We have two parts here. We have an LED with a side emitting lens, and the goal of this lens is to get as much light as possible coming out sideways, and as little as light as possible coming straight out. And the reason we want to do that is we're going to put that assembly inside of a reflector. So we want light to be coming out here, improve the collection efficiency of the reflector, but also try to cut down on the high luminance that you would see if a user was to look into this system right here. Let's say this was a little reflector or LED lighting assembly on an aircraft where you wanted the reading light. And if you looked up at it, you don't want to have that really high luminance from the LED itself. So doing something like this can have two effects. One is it can improve the collection efficiency of the lens, but also it can try to minimize that high luminance that you see. So the question is, in this case, is it better to optimize the lens and then put that in the reflector and optimize the reflector? Or is it better to make a single assembly, lens and reflector, and optimize them together? So let's take a look at that. If we're doing them separately, the first step we would look at is the lens. So here's the lens profile. It has two control points, here and here. These are spline curves. And these points can move in 2 axes each. Here, this box and this box. The goal is to have the light coming out as much sideways as possible. So we want light in the 45 to 80 degree range and minus 45 to minus 80 degrees, and then as little light as possible between those lobes. So here's that profile graphically. We want light from minus 45 to minus 80, 45 to 80, and ideally we'd have no light here in the center. So that's our goal for the first step. Here's the log. Notice after about 75 iterations, it had a pretty good result. And after 264, we stopped the process. And here's before and after. These are the candela or intensity plots. You can see we've got more light into these, roughly 45 to 80 degree lobes, because our intensity here went from under 20 to a little over 20. But also we've reduced a lot of the light here that was in sort of that center part. Now we still have some higher intensity peaks here that we could look to address, maybe try a slightly different design, but it is an improvement. And here's the before and after shapes. So again, we were starting with something that was close, and we improved it with the optimizer. So next step, we could add a reflector to that. And here's the reflector profile. Has 2 control points. Similar, not adding too many control points. The goal now is we want to have an even candela distribution from plus or minus 20 degrees and then falling off to 0 at plus or minus 25. I should note too, this reflector is faceted both in radial and azimuth angles. And there's the before and after. And we can see it's actually pretty good. It's relatively uniform through plus or minus 10 degrees, then falling off. Ideally we'd like to have it down to 0 by about here, but we still have a little excess energy out there. But a big improvement from where we started. Also notice the intensity change went from 0.65 up to 2.1. So 3 times the intensity with this reflector optimized. And then the before and after shots. So here's our optimized design. Now the question would be, could we do this in a single step? And we can. Here it is in the optimizer. We have 2 elements. The optimizer, there's no limit to the number of objects you can optimize at one time. So now we have 2 objects, a lens and a reflector. Our goal is the same as what the goal for the reflector was, which is uniform candela profile from plus or minus 20 degrees, falling to 0 at 25 degrees. Here again is our optimization log. The closer this gets to 0, the better. Stopped it after 231 iterations. And here's our before and after results. So we see we have a little more structure in here. Not bad, plus or minus 20 degrees, and pretty much falling off to close to 0 here at 25 degrees. But note that our intensity is down. Previously we had 2.1 candela, and down here we're at 1.6. Now these are just sort of normalized values. They're relative to each other, but not necessarily relative to real world numbers. But we had less intensity in this design. And before and after. And here's the resulting candela plots, the separate optimization and the combined optimization. So you do get fairly different results between the 2 methods. As you would expect, the actual designs are different. But one thing I wanted to note is this is a photorealistic rendering looking back into the 2 different reflector designs. And on the left, we have the combined result. And on the right, it was done, as it was done separately. And just sort of the one takeaway I have on this is you do have this much higher luminance spot right here in the center, as compared to that luminance is more spread out in this one here on the right. So a user looking back at this, if this is something that could get into your eyesight, this combined optimization, I think, did not do as good of a job as the separate optimization. Okay, one last example, and then we'll wrap the webinar up here. If we wanted to look at a reflector with curved facets, so if we had these convex facets here on the inside of this reflector surface, and we want to optimize this. Well, if you wanted to make prototypes of this reflector, it's going to be expensive. Depending on how you do it, is it molded? Is it hydroformed? Is it spun? Making a mold for each of these is going to be an expensive endeavor. So the more we can do in software, the better. So during the initial reflector, here's the initial profile, single variable. 2 axes. And in this one, we have 11 vertical facets, meaning this profile is going to be divided up into 11 flat segments. Usually you do the flat facets to try to improve uniformity. And then there's going to be 21 radial facets. So when we go around this way, there's 21 segments going around the reflector that way. The LED in this model was a 3D solid modeling with surface source properties applied. In this case, it was a Seoul Semiconductor, a Creech, like chip on board array here. The optimization goal for this exercise was even illumination across the central 2/3 of a target. And here's the results. Here's our error function, 166 iterations. Our best came at 156. In this case, we did get a bit of an improvement. It's not a large change, but we did smooth out if we look at the profile curves here. One thing I noticed, I'm looking down here, is my efficiency, or flux divided by emitted flux, went from 70 to 75.5%. So we got a little more light on the target, and we smoothed it out somewhat. So again, an application where doing physical prototypes of something like that could be difficult. And here's our 2 profiles, before and after. Okay, so just to wrap up, some of the advantages of doing things. So virtual prototyping for Luminaire designs using optical design and analysis software allows for a faster, more efficient design process. It can allow you to get better designs when compared to the trial and error process. Look at, if you remember the TIR hybrid lens, my design was actually much better with the optimization process than what I was able to get with trial and error. There's the ability to try multiple designs for minimal extra cost. You can sort of take a risk. Would this design work? It might be something off the wall or something you don't think will work, but it might be worth trying. You can do it easily in software. You just make the model, run the ray trace, and try it. It also allows for fast and easy analysis of those potential designs. You don't have to make a prototype, bring it into the lab, measure it, which ultimately can take days. And then lastly, the goal we always hope to see with this is a lower development cost. The faster you can bring the design to market, the less iterations you have to take, the less time getting things measured, the lower the cost of the development, potentially the higher the profit. I should mention, as you could probably see, we manufacture and sell TracePro here. If anybody's interested in trying the software, we do offer a free 30-day trial. So just visit our website at www.lambdares.com or contact us by the phone number or email addresses listed there. And we'd be certainly happy to talk to you about how you could use something like this to improve your design process. And that's, with that, I'd like to thank everybody for attending this afternoon. I think Robin is going to come back in here. We'll take a look at what questions we might have. So, Robin?
Hello, Dave, and thank you very much. And if you have additional questions, attendees, just please enter them into the question box. And we'll begin here with question 1. Question is, I wanted to do a startup in photonic and nanophotonic technology, but I am stuck because I do not have any photonic EDA tools. What advice do you offer me?
Well, that's a good question. I was thinking about this, Dave, because I saw this one come in. The thing is that in terms of EDA tools, and in terms of you're trying to analyze things on a very small nanophotonic level, and in that case, I believe that wave propagation would be a very large part of what you're trying to do. And if that's so, TracePro has Monte Carlo ray tracing in it, but not wave propagation. So I think you'd have to look at the wave propagation tools. Dave, what do you think?
I would agree if that's nanophotonics and things like that. There are some good ones out there, programs for that. That is sort of a difference between something like TracePro, which is doing Monte Carlo ray tracing versus wave analysis. So yes, I'd take a look at some of the wave analysis type tools for that type of an application.
I also see that there's a couple questions here of high priority that I'd like to get to first. The first question is TracePro capable of global optimization or only local optimization? And I think I can answer this one too, Dave, because I have a good background on what's going on here. Dave's been showing the local optimizer, which is the downhill simplex method. In the next release of TracePro 7.9, there's going to be a tolerancing utility in there that you can specify a high and lower limit, and the program will go through and do a tolerance study using a Monte Carlo technique. But we're also trying to get in the Global Explorer capability that is in Oslo into the TracePro 3D Interactive Optimizer. And we're hoping to get that in either the 7.9 or 8.0 release. Another good one for you, Dave. What if the lens is not a rotation of a profile like those you've shown?
You can certainly do an extrusion of a profile or a sweeping along a path. It does not have to be a rotationally symmetric profile. It could also be an asymmetric or a freeform design. I just didn't happen to show any freeform designs in this particular webinar, but you can do, it does not have to be rotationally symmetric. Could be extruded, could be swept along a 2D or a 3D path. It could be transformed if you're doing a light guide from one shape to another. So there's a lot of capabilities just beyond rotationally symmetric.
I've got another question for you, Dave. How can these algorithms be applied to area lighting versus directional lighting?
Same thing. You could, if you're meaning using existing fixtures and then trying to evenly light a space with a given number of fixtures, yes, the optimization routines can be used to, for example, move fixtures within a space and try to find the best arrangement for an even illumination. It involves writing a couple lines of a macro code, but it's a fairly straightforward process.
I've got another question about the photolistic renderings. How long did it take to produce the view-dependent photolistic image of the TracePro logo you showed in the webinar today?
Probably less than 5 minutes for that one. If I set the quality higher, it could take longer, but that one goes through pretty quickly.
Got another question for you. How do we specify the target shape and distance from the reflector in the optimization?
Well, what it does is it actually uses the model in TracePro. So in TracePro, you would have the reflector or the lens set up, and then you'd have a target placed where you're interested in the results. And you name one of the surfaces of that target. For example, surface could be named detector or wall, something like that. And in the optimizer, you tell it, I want to see the irradiance or the illuminance on that particular surface. So you set it up. The optimizer doesn't know what the distance is. That's set up and defined in the TracePro model.
I've got another question, and I think it's perfect for you, Dave. Does TracePro include source models for xenon short arc and metal halide lamps?
We do have some catalogs of things like Osram and some Philips, I think, HID type lamps. My background is actually, the reason Mike mentioned that, my background is xenon lighting. So typically, I've not found a lot of good models online for xenon lighting, so I've made my own. Usually that's the best way to go, because they can vary so much. But usually in a case like that, what you're going to be doing is making a 3D CAD model of the lens and then coming up with a good way to model the arc distribution from that.
I've seen you do, I think you've got a webinar on this, Dave, that you go through. I think it's on source, how to set up sources correctly with the different techniques in TracePro. I think you go through a whole model. So if you check the webinar section, I think, I don't know what the name of it is off the top of my head, but I think it's something like how to do accurate source models in TracePro.
It's along those lines. Also, if you search my last name for SPIE publications, I did a few papers a few years ago on modeling xenon sources in software. So that's probably still available out there.
I have another question from Matteo. If I optimize 2 or more elements, both, I reduce the computation time, but I reduce the efficiency of the optics too. Meanwhile, if I optimize one singular element, I can maximize the efficiency of all elements, but the optimization time is much longer, correct?
It's going to depend on the optimization. The one where I showed here, the combined optimization probably took a little less time than the separate ones, but the results wasn't as good. You're trying, you know, it comes down to, I think, the system and the goal you're trying to achieve. It's probably going to vary on a case-by-case basis. I don't think I can offer a general answer that will cover everything.
Yeah, one of the things I want to tell everyone out there is that there's a lot of webinars on underneath the support section of our website, and a lot of the questions you guys are asking, like, you know, is there a webinar on this? Is there a webinar on that? Yes, there is. We've got over 20 now, and they really encompass almost everything you would want to do in the program. Everything from 3D optimization to how to use the scheme macro capability in the program. So just look over there, look in underneath the header. If you have any questions about which is probably the best one, send off an email to sales. We'll be glad to answer that type of question. I got a couple of those, Dave. That's why I'm answering this like that. In terms of, can this process be done for optically coupled silicone optics? I've not made this type of work and typically get unrealistically low output efficiencies with my models.
I don't see why not. You'd have to, you know, take care in setting things up. So if you're using like the silicone as a filling mechanism, just so that you're always sort of filling a gap or coupling that way. So I think you should be able to, as long as it's, again, as long as it's things like you're doing geometric type ray tracing and not counting on, you know, diffraction or wave optics type effects.
Yeah, and one of the things, we have a customer who is fantastic at making silicone optics, and they've had amazing efficiencies out of making these lenses, but they've also spent years creating the process that makes really, really smooth optics. Because if you turn on your optic in a dark room and it glows all over the place, you've got a lot of surface roughness on that, and unless you eliminate that surface roughness and get down to an the SP1 type level on those surfaces, you're going to lose a lot of light in these particular optics. I just did a webinar on this. It's on the website now with photonics.com last month. So take a look at that one if you want to see a little bit about finishes and how those finishes can affect your design. I got another question for you, Dave. Is TracePro suitable for design of lenses and regular refractive optics like ZMAX?
It could be. It doesn't. What it lacks is the optimization or the merit function tools, things like MTF, spot diagrams, aberration analysis, that type of stuff. For that, we usually, at least in our suite of software, we usually recommend Oslo. We can do, if you're doing, where the optimization process in TracePro really comes into its own is when you're doing things that aren't covered, like, you know, you don't want to focus all the light into a single spot. You want to have a particular angular distribution, or you want to have a particular illumination pattern. Those are the types of things that are difficult or impossible to do in a lens design program. So we try to work hand in hand with using the tools as they're best designed, or for the tasks they're best suited for. So for lens optimization, I would typically go to Oslo, and then for more general optimization, things like illumination applications, I'd look at TracePro.
I've got a question on optimization. Can you optimize, I guess, on increased efficiency or set lighting to a curved task? And I think this is what he's talking about is what can you specify in the merit function in the optimizer, Dave?
Yeah. Oh, you can specify. There's probably 12 or 15 different operands. If you're looking to improve efficiency, then what you could do is set a flux operand where you want so much power or so much flux on a surface. If your light source was emitting 1,000 lumens, you could set the goal on your target. I want at least 750 lumens, or I want 1,000 lumens, and see how close it can get to that. You could also use operands in combination with each other, whereas you could say, I want 750 lumens, but I also want a uniform distribution of light. And the reason you might do that is if you specified just uniform illumination, the optimizer might take and spread the light out so much that there's actually no flux or very little flux on the surface. So you can constrain it in 2 ways, or more than 2 ways. I've had examples I've worked with that probably have about 7 or 8 operands in the optimization or the merit function.
Well, there's quite a few more questions, but I think we've got to wrap it up. It's been an hour now, and what I'd like to say is that this recording is going to be on the photonics.com website. You can view it at any time that you want. Also, there are underneath the handout section, you can download the whole set of slides for this particular webinar as well, so share them with your friends. We will answer all of your other questions in emails to you directly, since we have your names and we have your email addresses. Robin, or Dave, do you want to add anything else? And Robin, do you want to wrap this up?
I just want to say thank you to Dave, and thank you to Michael Govin for bringing in these questions. Michael is the VP of Sales and Marketing for Lambda Research. And so at this time, I'm going to wrap the webinar up, and the recording will be available shortly. And I'd just like to thank Lambda Research Corporation, our presenter Dave Jacobson, and all of our attendees for participating in today's webinar presented by Lambda Research and hosted by Photonics Media. Thank you.
Thank you, Robin, and thanks to everybody for attending.